Okay. So, example. Careless Carlton left a large pot of water boiling on the stove. And worse, a cast iron pan is bumped so that it is in solid contact with a pot and his glass fish tank, which was carelessly left next to the stove. Draw a linear graph of the sad situation to determine what considerations determine if Careless Carlton's fish goes from winner to dinner. So, temperature of pot of boiling water is pretty consistent, so we could say it's a temperature source, some constant temperature. And contact object allows it to conduct heat. However, the interface between these two objects is going to resist heat flow. So we call that a resistance, contact resistance R1. Heat will conduct through the pan, and it will also dissipate. Well, it will also so it will conduct through the pan. It will also lose some heat to convection as well, and also there will be contact. Tank is in water at room temperature, can be assumed to start. Now, that body of water can hold a significant amount of heat. Potentially, so can this pan, although I didn't bother with a C on there, but we could potentially call that a thermal capacitance as well. But definitely the water, its temperature will rise. Now, fortunately, there are heat to escape, so there's convection from the tank to the surrounding air. There's also conduction through the countertop as well. So convection, we'll say, is R5, and then conduction, R4. So let's draw a linear graph and see if that helps us decide. So, which we always we'll just call it T infinity room temp. And then we have a node associated with the temperature source. So T higher here, this is the temperature associated with the boiling water. We have resistances. I'm going to ignore convection from the pan here, the cast iron pan. That might not be a good assumption, but for this model, we'll do that. We could add a resistance, a convective resistance as well. But let's just say conduction to the pan, and then contact the tank. This one will be associated with a capacitance, C. And if it was just this, then whatever temperature eventually conduct through R1, R2, and R3, and we would get a boiling fish tank. But fortunately, there are these other pathways for heat to go from the tank. So heat can't just enter through this contact. It can also exit through R4, which is the conduction, and R5, which is convection. So what this comes down to is a balance between those two aspects. So heat coming in and heat flowing out. As long as we're pro Careless Carlton's fish here, not getting boiled for dinner. So we are going to say that we want low R4 and R5. Low resistance so that the heat can flow out and essentially this capacitor discharge to happen. And notice that R4 and R5 go to ground, and that's because the reference temperature between the tank temperature and T infinity out here in both cases. So the air temperature you can assume that the temperature of the cabinets or whatever, the counters are room temperature as well. So that's our solid. We would have to, of course, determine values of R1, 2, 3, 4, and 5, and the capacitance C is probably the easiest one to calculate in terms of those parameters. The source is consistent. It's boiling temperature, so not too much to worry about there, and it would all just come down to the relative resistances here. We can go through this process, and actually after the next lecture we'll do a couple examples of these problems all the way through the state equations. But the first part is to be able to draw the linear graph. Once the linear graph is drawn, it's the same process that we learned in volume 1 of the system dynamics, so for electronic systems and mechanical systems. So now same applies. We have source, D types, A type, and we can draw a normal tree and derive the state equations. So yeah, all right, I'll see you guys in class.